Hey, Intro to Calc, and welcome to Task 5.4 and 5.5. If you'll notice, this is one PDF, because I've kind of smashed the two tasks together, making them a little bit shorter. So hopefully this helps you get started. If you have not reviewed those exponent rules from last week, maybe have those out or go back and look at them. That's going to come into handy as we kick off 5.4. So here we go. I'm going to dive right into 5.4 by talking about our exponent rules. So we talked about these last week. We have something called the power rule, which tells us that when we raise a power to a power, we multiply the powers. That's going to come in really handy. That's why I'm mentioning that one first. So I'm going to put a star right next to that one right now. We're going to use that one pretty much on every single one of these problems. And then we have our standard, our product rule, which tells us that when we multiply two bases, same base, we're adding the exponents. And the quotient rule, when we divide two bases, same base, we are subtracting the exponents. But all that to say, let's kick off these problems. When I look at the very first problem, I see that I do have 3 to some power equals 3 to some power. Well, when I think about that logically, if both of these are 3 and they're equal to each other, then the powers themselves must also be equal to each other. So essentially 3 to some power has to be the same as this other power. So I can forget about the 3's altogether and say, well, as long as they're both 3, their powers have to be the same, because that's what that equal sign right there is saying. It's saying these two things are in fact equal. So we can just set the powers equal to each other. 2x plus 4 then must be equal to 12. Subtract 4 from both sides. Divide both sides by 2. And we find that x equals 4. I never trust this right off the bat though. I like to just kind of plug the point back in, verify that it does work. So 3 to the 2 times 4 plus 4 equals 3 to the 12. Well, 2 times 4 is 8 plus 4 is 12. So 3 to the 12 equals 3 to the 12. You could put those into a calculator or just take it for how it's written. That is, in fact, true. Okay, that works really nicely when we have the same base on either side. But what if we don't have the same base on either side? What if we have two different bases like we see right here? 100 and 1,000. 100 and 1,000. So these numbers feel really similar to me. They feel really actually almost like the same number because they have the same base number. What is that base number? 10. So if I can rewrite these both as 10 to some power, the same way the above problem was 3 to some power, I should be good to go. So for example, this one I can write as 10 squared, or 10 to the second power, still raised to the 7x plus 1. And this one I can write as 10 cubed, or 10 to the third power, still raised to the 3x minus 2. Now this is where that power rule is going to come in handy. Here's our power rule again. If we have a power raised to a power, we are multiplying those powers. So here I am multiplying the 2 to the 7x plus 1. Making sure to distribute it, I get 10 to the 14x plus 2. Same on this side. That 3 gets distributed to the 3x minus 2, multiplying. 10 to the 9x minus 6. Now we have that magical scenario from the problem above. When we have the 3's equal to each other, we can just solve those exponents. Same thing right here now. We have our 10's the same, so we're really just looking at this exponent here must be equal to this exponent right here. Or 14x plus 2 must be equal to 9x minus 6. So let's subtract. I'll get all the x's on one side. I'll get all the numbers on the other side, or all just the constant values on the other side. Divide both sides by 5. And there we go. I could plug this back in and make sure that it is exactly the same. It would require me to put it into a calculator, and that's totally fine. Just like we plugged it in above, that's a great extra check to make sure you've done the problem correctly. So you're going to want to approach the other problems the same way, but I want to give you a quick reminder before letting you go on these. If I have x to the negative power, any negative power becomes a fraction. And if I have x to a fraction power, let's say 1/2, that becomes a radical, the second root or square root of x. Don't forget these. These are going to come in handy when you're doing pretty much all of the problems like this. Okay, so pause the video right now. Try these out. I think a great asset of having this on a video and not just being live in the class is that, first of all, you can increase the playback speed, you can slow down the playback speed, you can rewind it, you can fast forward, you can pause. So right now, do that. Pause the video, try the rest of these. So hopefully you tried the rest of those. Check with me in office hours if you want to see the solutions or just check your work. Those problems all should have worked out nicely, meaning you could write both sides of the same base. But what happens when you can't? For example, on A here, 4 and 11, they're not the same. I can't write them both as anything with the same base. So what do? I need to rewrite this as a log. I need to rewrite it as a log. So let's start by doing that. When I rewrite something as a log, hopefully you guys got a chance to practice this in your Khan Academy last week. I know that my base remains my base. So when I'm writing the log, I'm doing log base 4. Well, log base 4 of 11 has to equal that exponent. I want you to always remember that our goal is the exponent. We're trying to solve for the exponent. So that's always going to be what we're setting equal to. X equals log base 4 of 11. I think if you always remember that the base stays the base, so 4 comes down here as 4, and that our exponent is the opposite side of the equal sign. You kind of always keep that in mind. You won't make as many mistakes rewriting this as a log. So now when we look at this way, we see really clearly, yeah, 11 is not a power of 4. It's just not. So we're not going to be able to do that. This is where we get to type it into our calculator. Some of your calculators just straight up, you can type in log base 4 of 11. Other calculators can't, and that's why we have the change of base formula, which just tells us the base goes in the denominator, the argument goes in the numerator, and we can use any log base we want. I like to use log base 10, which on your calculator is just log. But you could also use log base e, which is just ln. So let's rewrite this. This becomes log base 10 of 11 over log base 10 of 4, which we can put in our calculators. That is much more easily put into your calculators because you should have an ln or a log button on your calculator. So ln of 11 divided by ln of 4. And again, you can use log or ln, it doesn't matter. We get 1.73 and some change. Let's check, does it say how to round it? It doesn't indicate how to round it. If you look at your calculator, this should say 1.7297. We want to usually round to the thousandth place or the third decimal place, which would make this 1.730. So let's try another one. Let's try D. Before we can do anything with a log, we need to get this 2 to the x plus 1 all by itself. That needs to be isolated because that's what we're trying to solve. If you notice above, that 4 to the x was by itself, and that's why we could turn it into a log. So let's add the 5 to both sides to get that 2 all by itself. Now looking at this, hopefully you don't think, hey, 2 and 10, they're both multiples of each other. I can rewrite those. Multiples, no, don't work. We want powers, and the powers of 2 are 2, 4, 8, 16. This is not 10. 32, 64. Nope, 10 does not fit in here. So no, we cannot write these as powers of each other. And the x plus 1 is trapped in the exponent, so we can't divide this by 2. We can't do anything except a log. So same idea. Base stays the base, log base 2 of 10 equals x plus 1. And remember, the goal was to get that exponent out, to get that exponent on the opposite side of the equal sign. And now we have that. So let's keep solving because we still are just trying to solve for x. Subtract 1. Log base 2 of 10 stays all together. It's a number. We can put it in our calculator and find it. Minus 1 equals x. Well, there we go. We've solved for it. Now let's just put it in our calculator. If your calculator is not the fanciest calculator in town, you're going to have to use the change of base formula, which means we do the log of 10, that's our argument, divided by the log of 2, our base, and then subtract 1. So I'm going to do that now, and like I said before, you can either do log or ln, it doesn't matter. Log of 10 divided by, and if you're saying log of 10, that's easy, I can do it in my head. Yay. If you're not, don't worry. Don't worry. So log of 10 divided by log of 2 minus 1, 2.3219. But again, we're going to round that to this decimal place right here. So we want to round that up to 322. So on these ones, look for opportunities to do this without the change of base formula, but when you're stuck where you have to use the change of base formula, you'll notice. Okay, once again, pause this video, try these 4 problems right here, right now. Some of them need change of base, some of them don't. Pause the video, only start when you're ready to move on. Okay, before we move on to the last set of problems for this, I want to talk to you through some logarithm rules. So these logarithm rules should go right along with the exponential equation rules right at the top there, the exponent rules in general, product, quotient, and power. And if you notice, they have the same names, product, quotient, and power. So let's start with the product rule. For our exponential, it's exactly the same. Whenever we multiply 2 terms in a log, just like multiplying 2 bases, when we multiply 2 terms, we can add the 2 logs. Or multiplication inside of a log becomes addition once we expand the log. That's the product rule. Product meaning multiplication. Multiplication expands to addition. Quotient rule, whenever we divide, just like dividing 2 bases, we subtract the exponent. Well, dividing 2 terms inside of a log, we're going to subtract the 2 logs. We're going to subtract those 2 individually. I always like to remember that anything in the denominator, that's what's being subtracted. So those denominator terms, in this case the b, we're subtracting log b. And lastly, the power rule should match our power rule of exponents. When we have a power raised to another power, well, what did we do with our exponents? We multiplied. Same here. A power raised to a power means we are going to multiply that power onto the log. Multiply that power to the whole log. So keep these rules in mind as we try to solve some equations with logs. And again, I'm only going to do one of these, so come to office hours to see how the rest end up working out. I'm going to start with A. So on A right here, I notice that we do not have a standard log equation. I have two logs right here, and as long as there are two logs, I can't really do anything with this. I can't change it into an exponential equation because that's our goal, change it into an exponential equation. I'm going to write that out actually. Goal, change to exponent. As long as these two logs are separate, I cannot do that. So let's combine them. If you look at our product rule tells us that two terms multiplied expand to addition. Well, I've got addition right here. I've got this log plus this log. So let's kind of undo that expansion. Let's condense it, bring the logs back together as just one log base 2. Well, I'm going to write this a little bit smaller. Is 1 log base 2 of this first term right here, x minus 2, times the second term right here, x plus 5. So we took two logs that were added and we reversed it and we condensed it down into one log by multiplying the two arguments. Let's simplify this a little bit. I'm going to multiply this out. And now I do just have one log. If you notice, I have log of something equals that. So I have just one log. Let's go ahead and turn it into an exponent. Just like when we were going the opposite direction, the base stays the base. And just like when we were doing exponents, we're going to say the base to the power of negative 3 equals all of this. Oops, I think I actually added that negative in there. It should just be positive 3. Whew, that makes it so much nicer. Okay, so from here, we just need to solve this out. 2 cubed is 8. And if you're looking at this, don't be afraid. It is just a quadratic. Let's subtract 8 from both sides. And now I need to factor that out. If you guys thought we were getting rid of factoring, I am very sorry to tell you we are never getting rid of factoring. Check my work when you come to office hours. If I somehow, some way messed this up, it happens all the time. Let me know. But I think we end up with x equals negative 6 and x equals 3. So here's the last thing we need to check. When we plug these back in, we cannot take the log of negative numbers. We cannot have negative numbers there. So let's just kind of mentally plug these back in, or I'll write it out. If I were to plug in 3 minus 2 is 1. Cool, that's still a positive number. 3 plus 5 is 8. Awesome, that's still a positive number. And if you were to solve that out, you'd find out it does in fact give us 3. Let's try the other one though. Negative 6 minus 2, negative 8. Nope, can't have it. We cannot have that. So this solution does not actually exist. This solution is what we would call extraneous. We don't even need it. The only solution we want is that x equals 3. And with that, I'm going to let you guys try the last 3 on your own. Remember our goal. Our goal is to change to an exponent. So once we condense these logs down, we want to change it to an exponent. Come see me in office hours. Thanks, guys.